and see what is that we did on the previous class meeting. Does anybody keep a record of that or not really? Did we go to 2.3 already, or we're still in 2.2? That doesn't look familiar. Let me go to 2.1. I think we started to work on chapter 2 and we used to graph some functions, but let's see what exercise I asked you, I think, to find vertex of, like maybe problem number 2 exercise or something, to find the vertex of parabola. Well, let me do it so I can recall this. So in exercise number 2, if I take a function f of x and then do its derivative, so we have x squared added with 6x minus 3, and then I will take a derivative f prime and then set it equal to 0. So we're going to get 2x plus 6. So once I write this equal to 0 and solve this little equation, I will be able to find that so-called critical point. So we bring that 6 over to the right side as a minus 6. So x is equal to -3. So please notice that the graph will be a parabola that opens upwards, right? And what I need is to find the lowest point on this parabola, and I need to get its y coordinate. And to get the y coordinate, I need to plug this into my original function. But I guess that's not what I asked on the quiz, if I remember it right. I just asked you to find the x coordinate, and that was good enough. But one can continue, replace x with a -3. So we're going to get a -3 to the second power plus 6 multiplied by -3, and then subtract 3. So we're going to get a 9 minus 18 and minus 3, which is equal to -12. So once I have found the x equal to -3 and y equal to -12, then I can make a picture of that function that looks like will pass through point -3 on the y-axis, so it'll look somehow like that. So whenever you have so-called free term on the function, then this is your intersection with y-axis, and I just did exercise number 2. Graphed parabola. When you say, well, Alex, we graphed lots of parabolas already. And yes, to graph parabola, I need to get a special point called vertex. And the key idea of calculus is that when you find derivative or a tangent line, then when you set this equal to 0, you find a special point at which the slope of tangent line is equal to 0. So you get a lowest point on this graph, or minimum point. And that's really all we need, because the vertex does have the minimum at the vertex, at the point -3. So using these ideas, you can graph some other polynomial functions. Let's say exercise number 15, which deals with the function which is cubic, g of x, which is x to the power of 3 subtract 6 times x to the second power and plus 10. So I'm going to be taking first derivative of this function, and then also the second derivative of this function. We'll see why. So we're going to differentiate that derivative once again. So first derivative is 3x to the second, and then 6 times 2, which is 12, right? So it'll be minus 12x. And when I differentiate this again, I'm going to get a 3 times 2 is 6 with just first power of x and minus 12, because derivative of x is just 1. So I will set this equal to 0, both of those equations, and find special or so-called critical points by now solving those equations, and I will use factoring. So I'm going to take out 3x and have x minus 4 inside parentheses. So we're going to have either 3x is equal to 0 or x minus 4. And then there'll be two special points, or critical points, people say here. One of them is 0, right? 3 times 0 is 0, and the other is 4. And for the second equation, analogously, I'll get a critical point as well. And this is 12. Oh, this is 2, sorry. 6 times 2 is 12. So I'm going to need to make a picture of this function, capital G, of x at point 0, at point 4, and at point 2. Once I get the y coordinates of those x values, I will be able to make a picture. I'll just plot and connect these points all together. 0 is my favorite point, because when you use it, then everything turns into 0, and all you have is just 10. So this is nice. For the others, you could use calculator. Probably it's going to be the best way to go, not to make a mistake, because otherwise it's easy to get messed up. So 4 cubed is 16. Let me still get this answer. You could just put in the calculator. Then 6 times 4 cubed is not actually 16, it's 64, right? Should be careful. So I'll get a 64. And then minus from it 16 times 6. Is that 96? Something like that. And also plus 10. So what do you get? Looks like from 106, I subtract 64, get 42. Please double check if that's right. And then analogously with a 2, I get 2 to the power of 3 minus 6 times 2 to the second, and then plus 10. So here we have 8, and 10 is 18, and subtract 6 times 4 is 24. So this is something negative, like -6. Well, I got 3 very special points. So I'm going to make a picture of my cubic function. Third power is the largest. So how's it gonna look like? Well, let's see. At 0, we have 10, someplace up here, right? 0.010. Then at x equal to number 2, I got -6. So at 2, it's -6, someplace down here. And then when x is 4, then we got a 42. Okay, at 4, so all the way up someplace, 42 level. So connect these points in such a way that function is a third-degree polynomial. So what's so remarkable about third-degree polynomial functions? Well, they have so-called negative end behavior. One end goes down and the other goes up, just like for the cubic parabola for x cubed, which means that I have to have one end keeps going up and the other keeps going down. So it looks like this will be the minimum point of it. And notice that also this point 2, the minimum point, looks like is here. And let's see, let me double check. 8 and 10 is 18. That's -6. Yes, let me double check that one. It's 64 minus 96, right? So it's negative. It's something I didn't calculate correctly. It is what? Negative 32 and 10. It's negative 22, right? So that point is actually all the way down. Now it makes a little bit more sense. So it's not here, it's lower. It's at the level of -22. So please double check, because I guess this shows that calculator isn't that important to have, because now I can graph the parabola that goes upwards, just like my right end here goes upwards. And it starts here at 0 second derivative, so-called inflection. And then it continues from that point as a parabola that going downwards. So please notice that I kind of attached two parabolas to each other. One that was like going up, and the other piece that was the one like going down. See? Those are key points that we just found. First of all, point 2, where it inflects, where we change behavior from going up to going down. And we also found so-called minimum and the maximum points of this graph. And that's just amazing, isn't it? We found a pair of points, the lowest and the largest. And if you're dealing with some question that asks you where you can maximize your profit, then you will say, oh, here is the largest. Of course, if you don't consider the part that keeps going upwards, because that part may be higher, but if it's a restriction, then you could always find which one is the maximum, and it is at 0 first derivative. So this story is what chapter 2 is all about. So section 2.2 continues exactly the same types of exercises again, and it sounds that we didn't look at it last time, right? Because I got mixed up a little bit. So let me just do problem from 2.2. So you will see that it's not any different at all with the section that called 2.1, because exercises are pretty much same. They're also polynomial functions. So let me try something like, say, exercise 27. I select one with the fourth power for a change. So let's see how we can graph the fourth degree parabola, which is going to be analogous to x squared, right? The fourth degree, x to the fourth, is the one that has both ends that point upwards. Let me get some room and do the same steps for problem 27 as we just did for previous exercise. So it turns out these two sections actually compose in one big section that is talking about the same exact thing, graphing functions by finding the minimums and the maximums. And that's all about finding derivatives. So x to the fourth minus 4x cubed and plus 10, I'm going to find the derivative of it. And then once again, find the second derivative. So 4x cubed, right? And then minus 4 times 3, 12x squared. That's my first derivative. Analogously, I'm going to find the second derivative, differentiate this again. So 3 times 4 is 12 with x squared, right? And then minus 12 and 2 is negative 24x. So I'm going to set this equal to 0, both of them, and get those special critical points. We're using factoring. So 4x squared, the lowest power of x, I always factor out, and have x minus 3, right? 3 times 4 is 12. So I can see that either x is 0, that's from my first factor here, or x is equal to 3. I say, looks like that x equals to 0 is order 2, 0. Well, let's solve the second one and see what this means. We have order 2, 0. So I take out 12x, right, and have x minus 2 in the parentheses. And notice that order 2, 0 actually happens that 0 appears again as one of my solutions. So when we plot these 3 points, I'm talking about 0, 2, and 3, then I will be able to see better what this is all about, right? So let us do this. It's a little bit tedious, but having such nice numbers is definitely a pleasure to work with, because usually you don't get such nice numbers. Look at this. At 0, you just get 10, just free term, right? What happens at 2? Well, looks like you're going to need to subtract from 16 number 32. So it's a negative 32, and 10 is negative 22, looks like. Please double check. And then with 3, let's see what happens with number 3 here. Looks like we have 81 minus 4 times 8 is 32, and then 2. So 91 minus 32 is going to be something like 59, I think. Again, please double check. Okay, so the graph is what follows, and on that graph, it looks like we have both ends of parabola that have to point upwards. So I'm gonna have to plot what points? What are the pairs? Do you see them? When x is 0, y is 10. So my first point is with coordinates 0 and 10, or just 10 on the y-axis. The next point is when x is 2, y is negative 22. Okay, when x is 2, y is negative 22, someplace down below. Okay. And then last point will be with coordinates 3 and 59, all the way up above, right? 3 and then 59. So I put it someplace here, just for convenience. So both ends must point up. We'll keep this in mind and try to see how this is going to be possible for my function. And notice that here I have, let's see, 27 times 4. I don't think it's 32. See, I have difficulty with arithmetic today. It's let's see, 3 cube factored out 27, and it'll be 3 minus 1, so it's minus 27. So here I got a minus 27 plus 10 is going to be minus 17. Okay, so it's going to be minus 17. I think it's the best thing is just to put this in a calculator, because I guess it's good that I miscalculate these things to show you that if you take that scientific calculator, right, that favorite Desmos, you're never going to miscalculate. So let me show you how straightforward it is to use it. So I get 0 to the power of 4. One is Alex, you already calculate that. Yes, I did, but just to show you that it's enough to just enter that stuff once, and that'd be good enough. So then there's plus 10, and I got 10. Okay, so the first one is double checked. Next, I put number 2 instead of 0. So look at that. I just added it, and I entered 2, and see what happens. It's negative 66. So no wonder I feel that something is kind of fishy here, because it's not negative 22, it's negative 66. Okay, that's better, right? So let's see. Got that one. And then looks like I can also go for the last one. And analogously, looks like, oh, did I enter it correctly? I don't think I entered it correctly. So, and yeah, I didn't enter it correctly. So let me enter it correctly. It says, how can I fix that? It's going to be 0 away, right? So I just need to practice use a calculator. And I think you already much better than I did that, right? So it's 2 power of 3. See, I really had too much of good time, I guess, the weekend, and relaxed, over relaxed. That's no good. But anyways, so minus 6. Maybe I'll bring this up a little bit so I can better visualize it, right? So my point is going to be here, minus 6 and a 2. Okay, so I guess main thing is not to hurry. So the next point, since it's not a minus 66, but just negative 6. Okay. And then finally, the last one, right? The last one will be with what? 3. So again, I highlight that place, delete it, and put 3 here. And same thing with a 2. So instead of 2, I put 3. I'll get negative 17. So the last one I did right. Okay. But I better make a correct picture. So let me do that. It's negative 17 here. And a 3. So the point is lower. Okay. So once you have these 3 points, then you can actually get the graph with both ends pointing upwards. So I start at inflection and I keep going up like parabola that goes up. Then what happens? Then I need to put like a parabola that goes down. So I can imagine if it was continued like that. But it doesn't continue like that, because after inflection, the parabola again is opening up. So notice that there are 2 points of inflection, one here and the other is here. And that way I have my graph with all those points of so-called inflection, and they were zeros of my second derivative. So at point 0, even though it was also 0 first derivative, but function did not have a minimum or maximum because it continued, it just made that wiggly structure somehow, right? And that's what that order 2 actually stands for, which is interesting to think about. So I'm glad that you already feel good about these first derivatives, second derivatives, and I guess it's just a little bit time consuming, and that's really all it is designed for, to find the largest, the highest, and the lowest values, and that's about it when you sketching graphs. I'm looking at these exercises. I see just fourth powers and third powers. I don't see any other values here. Also notice that sometimes they say round your results, which means that you're not going to get nice numbers. And that's why I would say don't try to do every single exercise here, because some of them might not be very nice, which means that some of them may have fractional zeros, and that could give you lots of hard time. So I guess those problems you may just skip, and remember, I told you to do just like a couple, 2-3 exercises per section. So you don't have to really get way too deeply into it and just doing the same thing over and over and over again, because it is a little bit annoying. So what I want to do is maybe move on to the next page and take a look at the cases with so-called asymptotes, when we graph functions with various asymptotes. Those functions will look like the one on the picture. So notice that we have a break in the graph, and there is so-called asymptote or invisible wall to which my function approaches but never touches. That's asymptote idea. So looks like we can go to the story of finding various of those asymptotes. And it turns out there are 2 types of asymptotes that we're gonna really care about. One type will deal with vertical asymptotes, and the other type of exercises with horizontal asymptotes. So let me try to take a look at, say, exercise number 1 that deals with the function which is having an issue at its denominator. And the function in exercise 1, my denominator x minus 5 cannot be equal to 0. So people say the domain of this function is x minus 5 is not equal to 0, or I can translate this right away into x is not equal to 5. And this turns out to be a function that has a so-called vertical asymptote with equation x is 5. So when they have such an asymptote, then turns out there is another asymptote, which is going to be a quotient of numbers with x, or so-called coefficients. And that happens because the powers of x are actually the same. So y is equal to 1 is going to be the asymptote. That's actually what we do in the college algebra class. Did you have a chance to take a college algebra class? If not, it's fine. And I just want to let you know what it deals with. So when you have a 0 in denominator, and then if you have same powers of x and on the top and on the bottom of your fraction, then the so-called asymptote appears, the vertical and horizontal. And then what people do is they look for the intersection with x-axis. And definition of x-intercept is y is 0. Because for any point on the x-axis, the y-coordinate is 0. Sometimes they call this zeros of the function. In other words, I need to solve equation that says my function 2x minus 3 over x minus 5 is the same as 0, which is equivalent to say that only numerator is 0. The reason is that denominator is never 0, because we just noticed that denominator x minus 5 is not 0, so numerator must be 0 in that case. So I can see that x has to be equal to 3/2. And this is the only point of intersection of my function with the x-axis, because it's called x-axis intercept. So when I graph, I'm going to have this approach into the vertical asymptote downwards, and then continue like that along the asymptote. And the other piece of graph will be here. The other piece of graph will be here, because it cannot go down and go up, because it will hit my x-axis again. So that's the key observation. Since we have only one point of intersection with x-axis, which is 3/2, then my graph crosses it only once. So the other piece of graph must be up there. So there is no calculus in this exercise, because we just need to basically graph function using the asymptotes and helpful points. So it's interesting to realize that. So it's just a refresher of college algebra. So when you, for example, are looking at the exercise number 4, I can find vertical asymptote here. That's what this exercise is asking. It says x squared minus 25 must not be equal to 0, right? And this means that x squared is not equal to 25. So what x is not equal to in this case? Well, looks like it's either plus 5 or minus 5, because both numbers, positive 5 or negative 5, when I put them here instead of x, will give me 0 on denominator. So my domain says that x is not 5 and x is not minus 5, and that's actually pair of zeros of my denominator. So that's how we look for the asymptotes. So what about exercise number 8? What about those domain issues in 8? Well, again, I see denominator here, so I can right away say that it's not equal to 0, denominator, right? And then I factor it with, looks like 8, I factor with 4 times 2, right? So there are 2 problem values that we see here. It's minus 4 or -2. So these two are out and everything else is in. And at those 2 points, we have vertical asymptotes. So how about a little quiz for today? What about exercise number 2 for a quiz? Can you tell me a vertical asymptote for exercise number 2? Just put it in the chat. So that'd be our little quiz. Hope you're gonna enjoy it. Right. Let me stop to record.